Okay, so now we are going into the divergent part of the co-APGP, where we're going to derive, okay, the sum of first n terms of co-APGP. Okay, in the part 1 of the video, I have just said that the derivation is not easy. That's why I have a part 2 for those who are more mathematically inclined. And this co-APGP can come up not just in investment or anything. Is a very common mathematical model that actually comes out. So actually our CPF calculations of the interest also uses the co-APGP method. Okay, so let's go on to identify some pattern in this progression. I see that my yearly contribute, okay, based on this formula that I have of the end of the nth year calculations, I see that my yearly contribution, okay, is an AP, okay, where that particular year K, I increase by this amount, 6,000 plus 1,200 K minus 1, right? And then my investment amount gains 4% per annum. This means, okay, my common ratio or the factor is 1.04, right? So because I have already explained, in order to find the sum of the first n terms, I need to know how many years I actually had invested, so that I know how many years each of my yearly contribution with its regular investment earns the interest, right? So what happens is that in a particular year of that n years of investment, so in n years of investment, okay, a particular year together with my contribution and its interest earned, my general term TK actually becomes this: K minus 1 times the interest. It is going to earn m minus k plus 1 number of years of interest for this particular term. So that would mean if I want to find my total sum, Sn, okay, it is actually sum of k equal 1 to n of 6,000 plus 1,200 k minus 1, 1.04, m minus k plus 1, right? Which I have also explained that it's very difficult to do this. We will use an Excel spreadsheet, and the Excel spreadsheet can help us to do the derivation of my total invested amount. So in any case, if I were to change this into a theoretical question where I want to compute, okay, my rate of my sum of n terms, okay, I will change this to my A, okay, this would be my D, and this would be my rate, 1 plus R over 100, right? And the rest is the same. But for simplicity, okay, I'm not going to use 1 plus R over 100 because it's cumbersome to write. I will just call it a capital R. Okay, to signify it is the 1 plus how many percent growth per year. Okay, so that it looks a bit easy. Okay, so it doesn't really matter to us what we have. So I can transform this whole Sn into n k equals to 1 A plus k minus 1 D, okay, times R to the power of n minus k plus 1. Okay, so now I would say that k is like my dummy variable. So anything that do with n inside this summation is actually a variable, as in a constant. So what happens is, let me just simplify this as much as possible. Because r to the power of n plus 1 is going to be a constant, I'm going to pull that out directly. Okay, and then I have a minus d times plus k times of d r power negative k. Right? So I throw everything else away. I just need to concentrate on this term. Okay, because if I know what this term is, I'm just going to plug back r plus 1 into it. It doesn't really matter. Right? So let's examine carefully this term. R power minus k. And then I also have this term kd, okay, times r power minus k. So this term here, we recognize that this is going to be a GP. Why? Because a minus d is a constant. R is also a constant, so what is changing is k. So when k equals 1 is r power negative 1, then r power negative 2, r power negative 3, you can see that this is a GP. So this is easy to actually settle. This term is not that easy. Okay, let me isolate the d, and we only look at k times r minus k. So if we look at this term, okay, I am not sure what it is. Never mind, let's write out a few terms to see. So this is d times 1 r power times 1 power negative 1 plus k is 2 r power negative 2 plus 3 r power negative 3 plus 4 r power negative 4. Now, what you realize is that this is not good at all. Reason, it looks like a GP, but somehow it is not one, because the coefficient doesn't work in a GP. You think that it is a AP, the coefficient does goes in the AP, but I have these R's. So that's why this is actually quite difficult for us to handle. Okay, so before we actually talk about this, okay, let us look at an easier case of things. Okay, what do I mean by easier case? Okay, I further simplify this into d and n equal 1 k r power negative 1 power k. So now I let the k power r power negative 1 okay be x. Okay, so now things looks a bit easier. Why? Okay, I'm going to again just look at this portion. Okay, so I'm going to take this out and look at it in detail. One thing that I know is that Sn, okay, of a GP, okay, that looks like that, okay, is equals to x plus x squared plus x cubed plus x power 4 dot 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 until x power n. The GP formula tells us that it's xn minus 1 over x minus 1 as long as x is not 1, right? So if I were to look carefully at this sequence and I differentiate it with respect to x, okay, so when I differentiate x, it becomes 1, 2x, 3x squared, 4x cubed, and x power n minus 1 equals to differentiate of this thing. Okay, and I see that this is summation differentiate x power k, which gives me n summation k equal 1 kx k minus 1, right? So what this tells me is that if I want to get this series, what I need to do is I just need to multiply x to this, which then tells us summation of k equals to 1 of kx k minus 1 is equal, xk is equals to x times this series, right? Which is going to be the same as x multiplied to the differential of this. Right? And all we need to do is to differentiate this and multiply x to it, which is easy because I differentiate this xn plus 1 minus x over x minus 1. And I'm going to use quotient rule on this. Keep the bottom, differentiate the top, x power n minus 1, okay, and then minus, keep the top and differentiate the bottom, divide by x minus 1 squared. So now I just need to expand and simplify. n plus 1 x power n plus 1 minus x minus n plus 1 power xn plus 1 minus xn plus 1 plus x divide by x minus 1 squared. And I will see that this x cancels this x. This n plus 1 minus 1 time of this n plus 1. And I'm going to be left with x times nx plus x of n plus 1 minus n plus 1 power xn at 1 divided by x minus 1 squared. Right? So we already said that the x is equals to r power negative 1 here. I can put everything I have in place. So my original expression that looks this complicated okay, this is my Sn, right? It's going to become R, sorry, here is N. So this is N here, Rn plus 1, okay? N plus 1 multiplied by summation k equals to 1 a minus d power r minus k plus summation k equal 1 take out a d, k r power negative k. Right? So we have already said that this is a GP. Okay, the first term of the GP is a minus d r power negative 1. My common ratio is r power negative 1. So I will get rm plus 1 a minus d r power negative 1. This is my first term. I have r power negative 1 power n minus 1 divided by r power negative 1 minus 1 plus d. I know this series to be exactly this, but x replaced by negative 1, right? So d times r power negative 1. As whenever I see x, I will replace it with r power negative 1. So n r power negative 1 n plus 1 minus n plus 1 r power negative 1 n plus 1 divided by r power negative 1 minus 1 squared. So if we were to put things in nicely, I will just copy down everything and rewrite it slightly. R power negative n minus 1 over r minus 1 minus 1 plus dr power negative 1 and r power of negative r n minus 1 minus n plus 1 r power negative n plus 1 divided by r power negative 1 minus 1 whole thing squared. And then we are done. So although it looks very terrifying, but if we have sub in n equals to 8, a equals to 6,000, d equals to 1,002, and r equals to 1.04, you should be able to verify that this is going to be the same answer as the Excel sheet. So this is the second part of the coAPGP. Thank you.